Hi everyone, welcome to Chapter 2, Section 2. We are doing Part 2 of Section 2 today because this is a little longer of a section, and it's super important for us to know this section because we use this for the rest of the year. So for today, we are finding areas under the normal curve without the empirical rule. So what I mean by this is the x values that we're going to use, they don't fall exactly on like a specific standard deviation. So the example I'm going to use is that for today, I kind of made this up, but the heights of West Broward students are normally distributed with a mean of 65 inches and a standard deviation of 2 inches. So this is the data I'm going to use for today, for all of our problems today. But another way we can write this, like shorthand style, because, you know, mathematicians are lazy people, so we like to use symbols. So another way to write that it's normally distributed, we can use a big N and then parentheses to signify like this is normally distributed, and then the first number that goes in it is going to always be the mean, and then the second number is the standard deviation. So just seeing something where it says n parentheses 65 comma 2 tells people that this is normally distributed with a mean of 65 and a standard deviation of 2. So the first thing I'm going to do is draw this out because that always helps me figure out how to, or what areas I'm looking for. There it is, beautiful. Took me a couple tries, but we are trying to find a probability this time. So I'll write it with my probability notation. So we're trying to see the probability or the proportion of people, of West Broward students specifically, who are less than 62 inches tall. So hopefully there's not too many, because 62 inches is what, like 5'2"? Kind of short for a person, but on average. But if we're looking for less than 62 on our picture, 62 is not one of our specific numbers for our standard deviations. So it's a little bit awkward because we can't really use the 68, 95, 99.7 rule. Because 62 is here. If we're looking for less than, we are shading all the stuff to the left. Okay. So the more specific way that we want to do this now is actually to use our z-scores. So remember we talked about z-scores as like a standardized distance away from the mean. So if we can calculate our z-score for 62, we would subtract our x value of 62 from the mean of 65 and divide it by the standard deviation of 2. Because if you remember, the z-score formula is x minus mu over sigma. Okay, so doing that, we end up with negative 1.5. Okay, so we're basically saying 62 is 1.5 standard deviations below the mean. Cool, which makes sense because according to our little picture, we are below the mean of 65, but now we know exactly how many standard deviations away we are. And with this number, now we can calculate an area using a special tool. We call it Table A because that's what your book calls it. So it's basically a table of all of the areas underneath the normal curve calculated already for you. Somebody out there did it for us. So all we have to do is use that table. So I've included the table here. This is the table that you will see on the AP Statistics test. It will be provided for you. So this is the one we want to be able to use. So as you can see, there's 2 pages to this table, and I kind of focused on this first one, so I made it bigger so that this is the one that we're going to use because as you can see, we've got this big picture at the top. This is the normal curve and it's shaded for us. So in both of pictures on both pages, the left side is always shaded. So basically it's telling you whatever area you're looking for, this table will tell you areas to the left if you shade to the left. And then underneath, we've got a bunch of numbers. The most important column that we need is the very left side. At the top it says Z. So this is like the beginning of our z-scores. And then same thing on the other page. So the first page that we're looking at here on the left, this is where all the z-scores are negative. The second page are z-scores that are positive. So that's how you're going to differentiate between the two and know which page to use. So on the first page with negative z-scores because we calculated ours to be negative 1.5. So if we're looking for a z-score of negative 1.5 on our chart, then we are going to go down the z-score column until we see negative 1.5 here. So the rest of our columns up top are going to be the second decimal place. So we only have one decimal place because we have negative 1.5. Technically, like negative 1.50 is our second decimal place. So the second decimal places up here would be 0 for us. So we're going to look at negative 1.5 here. If we had, say, like negative 1.57, then we would go all the way to the right until we have a second decimal place of 7, and then that would be our percent there. But we are not looking at that one. So negative 1.5 with a z-score of negative 1.5, the percent or the proportion that we're going to be looking at is the 0.0668. So going back to my original problem of finding the percent of people who are shorter than 62 inches tall, the proportion of that ends up being 6.68% based on our table. And again, you can answer with either the decimal or the percent. It's up to you. They mean the same thing. So that's how we're going to use our table A. So when we use this table, we want to make sure that originally in our original problem, we were looking for specifically that x was less than 62 because our table tells us less than values. So let's try an example where we're not doing less than then. All right, so this time let's do finding the percentage of people who are taller than 63.5 inches. So this time, we know we're not going to have like exact standard deviation values for the empirical rule. So when we draw our normal curves now, we don't have to label every single standard deviation, the 3 lines to the left and to the right of the mean. So our faster way to draw these out is just to label your normal curve with the mean and the standard deviation as just like a line across, and then place your x value that you're looking for. So for us it'd be 63.5, where it should be appropriately, because 63.5 is less than 65, so it'll be towards the left. And then because the symbol that we're looking for is greater than, we're shading to the right. So for every problem that we do of these, we want to make sure we draw the picture. Not only is it helpful for us to just visualize what we're doing, but also it is something that they look for on the AP test. So they want to make sure that you are using the correct numbers, and one way to show that is by doing the picture. Okay, so once we have it shaded in, our first step is to find the z-score. So we're going to calculate the z-score of 63.5 minus our mean of 65 divided by our standard deviation of 2. And when you do that, you end up with negative 0.75. Okay, so we have a z-score. Our next step is to use the table. So again, we have a negative z-score, so we're going to use the negative table, or the negative page of the table. So negative 0.75, we have 2 decimal places, which means our first decimal place is negative 0.7. So we're going to go down the left side column of the z-score table to look for negative 0.7. And then that's right here. Our second decimal place is the 5. So that's this column here. So where they crisscross right here will be our answer, or will be what number we use for our answer. So the z-score of negative 0.75 corresponds to 0.2266. But remember, our Table A only tells us areas to the left. So really what we're saying is, in our picture, if we were to shade to the left of 63.5, that would give us 22.66%. But that's not what we want. We want the area to the right. In order to find that, we know the entire curve, if you shaded the whole thing, that would be 100% shaded. So if we just take our 100%, subtract the 22.66% from it, then that'll give us the rest of the curve. So if I just do 1 minus the 0.2266, that'll give me the percent for the right side. So when we subtract, we end up with 0.7734. So finally, what our answer means is that 77.34% of West Broward students are taller than 63.5 inches. So for this problem, notice how I drew the picture, used numbers to calculate my answer, and then answered with a sentence. When we do these types of problems, we want to use all three of these things. So think numbers, pictures, words. Those are the things you need to completely answer a question. We want to have all these three things because on the AP test, we want to make sure that we answer completely by using words. And then finding the numbers, it's a math class, obviously you're going to use numbers. The picture helps to show that you understand what you are doing with your numbers. And so the visual aspect not only helps you to make sure you're finding the right shading, stuff like that, but also it gives the reader more information about what you're trying to do. So, in general, numbers, pictures, and words. So, next example I want to do is with the percentage of people between 61.5 inches tall and 66 inches tall. So this notation right here where you have x in the middle, x has to be greater than 61.5 but less than 66. So between. So I drew out my picture again because, you know, numbers, pictures, and words. So here's my picture. I have the mean labeled, standard deviation labeled, and then my 61.5 and 66 generally in the right spot. It doesn't have to be exact. We just want to make sure we see visually where we're shading. So we were saying that it's going to be in between. So everything in between 61.5 to 66. So when we find this area, keep in mind, using our z-scores and our table only tells us areas to the left. So for whatever z-score the 61.5 is going to give me, I'm going to have to find another z-score for the 66 inches. So with these problems, since we have two numbers, find two z-scores. So I'll start with that. So I found my two z-scores for the 61.5. It came out with a z-score of negative 1.75, and with 66 came out with a z-score of 0.5. So now, when I use the table, when I look up negative 1.75, the table will give me the area to the left of the 61.5, which will be this area right here. Okay, not really what we want, but we're still gotta look this up anyways. So the area to the left for a z-score of negative 1.75 on the table, here is the negative 1.7, and then the second decimal place was the 5, so that gives us 0.0401. Okay, let me just write that down really quick. 0.0401. Okay, I'm going to do the same thing with the second z-score, so 0.5. This one is a positive z-score, so I'm going to be on the second page now. So on my second page of the table A, 0.5 is right here. My second decimal place is a 0, so we're just looking at 0.6915 as our area. Okay, so looking at our shading, because the area to the left for the negative 1.75 z-score is this blue area that I colored in over here, but for the 0.6915, that's everything to the left of 66. So if I want this middle portion without that blue section, then all I have to do is take the area left of 66, subtract out that blue area, and that'll give me the middle portion. So if I take 0.6915, minus the 0.0401, that should give me that middle section between 61.5 and 66 that we want right here in the middle. So when I subtract that, I end up with quick subtraction skills right here, 65.14%. So again, answering with pictures, numbers, and words, we've got our picture, We've got our numbers and our words. 65.14% of West Broward students have heights between 61.5 inches and 66 inches. Done. So far we've talked about how to find areas under the curve for when you have less than, greater than, and in between areas. So those are like the three types that you'll see when we're dealing with finding z-scores using table A, or finding areas using table A after calculating z-scores. The other types of problems I call backwards problems. So with backwards problems, they're going to ask you or they're going to give you the percent that they want under the curve, and then you have to find the actual x value, or like the original data point. So a backwards problem could sound something like this. What height would be considered the 80th percentile? Still using the same set of data as before. So 80th percentile, remember percentile means that percent is below you. So if I were to draw this picture, my mean and standard deviation, obviously still the same. But they've given us the percent because they've asked for the 80th percentile. So 80% is what we're looking for. So I'm going to take my picture and shade as close to 80% as possible. So 80% below you means that you're going to be shading to the left, because those are all the heights that are less than you. And then I'm just going to call that 80% or 0.8, however you want to write it, up to you. Okay, so basically we are solving for that x value right there. We don't know what height that is because that's what we're trying to find. So we're going to use our tables backwards. When you look back at your tables, hopefully you see that we should be on the positive side of the table A because we have shaded more than 50% of our normal curve, which means that your z-score should be positive. So since we are given a percent, we are looking in the middle of the table where all the crazy decimals are because we don't have a z-score. That 80th percentile is not a z-score, so we're not using that z column just yet. We are looking in the middle and we're looking for the number that is closest to 80%, so 0.8. If we look here, it looks like we get pretty close right in here. Like these two look to be the closest. Okay, because we've got a 0.7995, that's pretty close to 0.8, and then a 0.8023, also pretty close to 0.8. But which one's closer? So the closer one would be the 0.7995 because that's only 0.0005 off versus the 0.8023 is 0.0023 off. So we want to choose the one that's closest. So for the 0.7995, the z-score that corresponds to that is this one right here. So looking at our z-score now, we've got the 0.84. So that's the z-score we're going to use, and that's how we use the tables backwards. So for this problem, with 80% to the left of our z-score, that z-score that corresponds will be 0.84. Now that we have a z-score, we can use the z-score formula to solve for x. So remember, our z-score formula is x minus mu over standard deviation. We know what z equals, 0.84. So then we can plug in our mean of 65 and our standard deviation of 2 and solve for x. So I'm going to multiply both sides by 2 to get 1.68, and then I'm going to add 65 to both sides. To get 66.68. And of course, answering with pictures, numbers, and words, we've got our picture here, we've got our numbers, and then our words. You would need to be 68.68 inches tall to be the 80th percentile. So this time I want to do another similar example. What height would be considered the first quartile? If you think back, your first quartile is Q1. So what percent is below Q1? It's your first quartile, so it should be 25% because, a quarter. So we know for our picture then, when we draw it out, we should have 25% below you. So with a mean of 65, standard deviation of 2, shading 25%, again, I'm just going to estimate. It's like right there-ish. So that area is going to be 0.25 because first quartile is 25%. Okay, so now we just need to figure out our z-score by looking at the table. With 25% on the shaded to the left, our z-score should be negative because we are on the left side of our mean of 65. So we know our final answer's got to be a number less than 65. Looking back at the z-score table, on the negative side, we are looking for the number that's closest to 0.25. So just going to get rid of some of my other markings first. Looks like 0.25 is pretty close here. And I don't know if you've noticed, but the numbers do go in order. So that helps usually. I think right here, between those two. So we want to figure out which of those is closer to 0.25. So between the 0.2514, that's about 14 off, and then the 0.2483 is about 17 off. So the closer one would be this one right here, the 0.2514. So that corresponds with a z-score of negative 0.67. Okay, so now that we have a z-score, now we can solve for x. So solving that out, we get a height of 63.66 inches would be considered Q1, or the first quartile. Finally, the last thing I want to talk about is the normal probability plot. Kind of playing around with fonts here. But the normal probability plot, what it does is tells you whether your distribution, your set of data, is approximately normal. And so in real life, it's really hard to get something to be exactly normal, but we want approximately, because once it's normal, we can use all of our calculations with z-scores and stuff, and our table A to find percentages. And so we want things to be approximately normal. So a normal probability plot will be able to show us that. Alright, so in this example, we've got measurements that describe the usable capacity in cubic feet of a sample of 36 side-by-side refrigerators. So it's those refrigerators that open like this. Are the data close to normal? So here's all the data. I calculated some things already. So the mean is going to be 15.81, and then the standard deviation is 1.19. So in order to make a normal probability plot, what we need to do is calculate the z-scores for every single data point, which is a lot. We have 36 data points here. That takes a while. So what we're going to do instead is use our fancy graphing calculator to do this. The first thing that we want to do is to type in all our data values into a list. Did that. The second thing is, in order for a calculator to do everything for us, we're actually going to use this list and tell our list number 2 what to calculate. So I'm going to scroll all the way up until L2 is highlighted, and then I'm going to type a little formula in here so that it'll take my numbers from L1 and find z-scores for me. So we know the z-score formula is x minus mu divided by standard deviation. So I'm going to type in, for my x values, it's everything in L1. So I'm going to do parentheses L1 minus my mean of 15.81. And then I'm going to take that divided by our standard deviation of 1.19. Okay, once you have that typed in, then when you hit enter, it'll automatically take each of your data values from L1 and do the little calculations that we typed in and give you the z-score. So here we go. Enter. Oh my gosh, all my z-scores. So it does it for you, which is great because that would have been really tedious to do on our own. Once we have z-scores, these are what we're graphing out on a normal probability plot. When we set up a normal probability plot, the x-axis is going to be the x values that we have, so our data points, and then the y-axis is z-scores. So if our x-axis is supposed to be our data values, our x values, and our y-axis is supposed to be z-scores, right now we basically have that set up already in our graphing calculator. Our L1 is all our data values, our L2 are all our z-scores. So if we can get our graph set up from the calculator to do it for us, then that would be great. So we're going to go into stat plot, so second and then the y equals button. We're going to turn on plot number 1, so make sure on is highlighted. And then here we're going to choose this first one, which is a scatter plot, because we're basically plotting points now, coordinates of x comma y. So make sure the first one is chosen, so hit enter. Xlist is our x variable, which was our usable capacity, which is our L1 data values. Ylist are our z-scores, so that's where we did all our L2, so that's all correct. Marks, choose one. And then instead of just hitting graph, because right now we don't have, our window set up properly, we want to make sure we go into zoom number 9 for zoom stat. Beautiful. Look at it. This is our graph. So with a normal probability plot, to sketch this out, because obviously our calculator can do it, to sketch it out though for answering questions or whatever, we just want to kind of estimate. It doesn't have to be super exact when we draw this out. So I'm just going to use the trace button, and so it'll kind of, I can scroll left and right to see what numbers we have, but it looks like our lowest number is 12.9 with a z-score of negative 2.44. So on our x and y axis, I know normally the corner of our x and y axis is usually 0, but we're just going to do a little break to show that we're starting at negative 2. I'll call it negative 2.5 so it gives me space. Actually, I'm going to make this a little bit nicer. And I ran out of space already. Cool. Okay, so you get the gist. And then we'll start at, I think it was 12.9 was our first data point, and it goes up to whatever. Our highest was 18.4. So we just need to be like kind of consistent here. Pretend you have your increments set up correctly, and then you're just gonna sketch out about what your graph looks like from your calculator. So it doesn't have to be super duper exact, but once you have the general shape, that's really what we're concerned about. Pretend I drew all the dots, blah, blah, blah. Okay. But what we are looking for in the graph is that we want pretty much a straight line, which we kind of have in this graph, because a straight line is going to tell us that it's approximately normal. So that's the most important thing to look for. So if it is exactly straight, it will be normal. If you see kind of a curve to it, or like either curved this way or this way, then it'll be skewed. So excuse my terrible handwriting. All right, skewed right or skewed left. So this is what you're looking for when you make a normal probability plot. Obviously, we want a straight line. It means that your z-scores are kind of all spread out evenly, and it increases by the same amount with the rest of your data, which shows a normal distribution, and that's what we're aiming for. All right, that's it for this section. That's it for this chapter. So thanks for watching. Bye.